Hey everyone, in this video we're going to talk about molecular shapes in the 3D model. So let's go ahead and get started. So all of the Lewis dot structures, all the single, double, and triple bonds that you've been drawing can also be represented in a 3D model. You can represent these with ball and stick models, the springs and balls, marshmallows, gummy bears. There's a variety of different ways that you could build these to show the actual bond angles. I'm going to go through the different types of molecular shapes today. The first thing you want to know is this is all based off of the VSEPR theory. VSEPR stands for valence shell electron pair repulsion, which is why we call it VSEPR for short. The electron pairs must orient themselves in order to minimize the repulsive forces. So, in other words, the electrons are all negatively charged and don't want to be next to each other, so they have to find a position that's the most comfortable. So the lone pairs want to take up a lot more space, so they're going to push everything else away. There are a couple types of bonds that you will see here. The bonding pairs are the ones that are going to form bonds or be represented by the lines. The lone pairs are your non-bonding electrons, and they're represented by the two dots. The lone pairs are going to repel more strongly than the bonding pairs, so they need to take up a lot more space. And because they take up a lot more space, they're going to reduce the bond angle and make it a lot smaller. You're going to see what I mean in a couple drawings coming up. So here we have an example of a drawing CH2O. So our bonding pair are our single lines right here, which is the bond, and our lone pairs are two dots. Notice that whenever we have the lines, they can also be represented as dots. So since this is a double bond and each line is 2, it would have 4 electron pairs. Okay, if it was a triple bond, there would be 6 here. So how do you find the molecular shape? The first thing that you need to do is draw the Lewis diagram. The second thing you want to do is count the number of lone pairs and bonds on the central atom. Just make a note that even though there could be double and triple bonds, it only counts as one single bond. And the third step is to determine the shape based on the number of lone pairs and bonds. I'm going to go through a few of these examples with you. Our first example is linear. Linear has 2 total bonds, 2 bonds, and no lone pairs. An example would be BeH2. Now I like to organize all of this information in a nice chart such as this. I like to put the type in one column, the degree angle, the bonds, the number of bonds, the lone pairs, an example of the picture, and then an example of the bond here. You can make this diagram as well if you wish. So like I said, our first one is linear. An example is BeH2. So when you do this, you always look at the center atom. So Be is the center. You have one bond on this side, another bond on that side, so that equals 2 bonds. There are no lone pairs on beryllium, so 0 plus 2 is 2. If you use the chart or what we just learned, you know it's linear. Our second example is trigonal planar. It has 3 total bonds, 3 bonds, no lone pairs, and it's BF3. An example, like we said, is BF3. We always look at that center atom. Boron is our central atom. We have 3 bonds, 1, 2, 3. There are 3 bonds. There are no lone pairs on boron, so the total is 3. The lone pairs on fluorine do not count when taking into account for the molecular shape. Our next shape is bent. We have 3 total bonds. 2 of those bonds are bonded with other elements and 1 is a lone pair. So for example, SO2. Here we can see SO2. S is our central atom. We have 1 lone pair on sulfur. We have 1 bond on the left and another bond on the right. 1 plus 2 is 3. Now remember, even though this is a double bond, it still only counts as 1. So that's how we got the 2. 1 plus 2, 1 plus 1 is 2. Our next shape is tetrahedral. Tetrahedral has 4 total bonds. 4 bonds, no lone pairs. Our example is CH4. Here we have CH4. Carbon is our central atom. We have 1, 2, 3, 4 bonds that surround carbon. No lone pairs on carbon, so we would have a total of 4. Our next one is trigonal pyramidal. We have 4 total bonds, 3 bonds, and 1 lone pair. Notice that whenever we have a lone pair, it looks much larger on the picture because they take up more space and they push everything else down. Our example here is NH3. Here we have NH3. N is our central atom. We have 1 lone pair. We have 3 bonds, 1, 2, 3. 1 plus 3 is 4. Our next one is bent. We have 4 total bonds. You have 2 bonds, 2 lone pairs. We could see the lone pairs, they take up much more space. They are much larger. Our example is H2O. Oxygen is our central atom. We have 2 bonds, 1, 2. 2 lone pairs, 1 lone pair, 2 lone pairs, so 2 plus 2 is 4. Our next one is trigonal bipyramidal. We have 5 total bonds this time. We have 5 bonds, no lone pairs. Notice there's no big bulges or no lone pairs. Our example is PCl5. We have phosphorus in the middle, that's our central atom. We have no lone pairs on phosphorus. We have 1, 2, 3, 4, 5. So 0 plus 5 is 5. Our next one is octahedral. We have 6 total bonds. 6 of them are bonds. There are no lone pairs. Our example is SF6. Sulfur is our central atom. We have no lone pairs on sulfur. We have 6 bonds. 1, 2, 3, 4, 5, 6. 0 plus 6 is 6. All right, today we went over all the different shapes that all the molecules could have. The best way to learn this is to do practice drawing the Lewis structures, practice identifying the shape by doing the lone pairs, the bonds, and the total, and using the chart that you have to identify the shape. Let me know if you have any questions.